online FDP program. So we will start with a small introduction, sir.
Yes, sir.
Yes, sir.
Good morning to everyone. I welcome our resource person, Dr. S. Thirumalai Kumaran. Is a professor of Mechanical Engineering at PhD Institution of Technology and Applied Research, Coimbatore, with the extension experience in the advanced manufacturing and sustainable machining technology. He earned his PhD in Mechanical Engineering with specialization in tribological and machining studies of aluminum-based hybrid metal matrix composite. He has more than 18 years of teaching and research experience. He has significant international research exposure, having several as visiting professor at Wuhan University of Science and Technology, South Korea, and international research professor at Yangon University, South Korea, where he worked on advanced machining and precision manufacturing technology. His research focused on hybrid machining process, sustainable and green manufacturing, advanced material processing, additive manufacturing, micro machining, and metal matrix composite. He has made significant contributions to the development of advanced and sustainable machining strategies through experimental, analytical, and data-driven approaches. His recent work integrated artificial intelligence and machine learning technologies for the process optimization and performance predictions in manufacturing systems. He has authored over 135 peer-reviewed international journals publications, accumulating over 3,200 citations with an Hutch index of 30. He has edited several international recognized journals and also that recognized book published by CRC Press, Taylor and Francis, Wiley, and IGI Global in the area of sustainable machining and green manufacturing. He has also contributed many more book chapters and reviewed articles in advanced manufacturing technology. He has successfully completed multiple externally funded research projects supported by national agencies, including BRNS, UCG, and CVRD, DRDO, focusing on advanced machining and materials processing. He holds a grants Indian patent and is a recognized PhD supervisor under Anna University, having gates several doctorates and postdoctorate research scholars. Dr. Thirumalai Kumaran serves on editorial board members and special issues editor for several international journals and actively collaborated with global research in Asia and Europe. He has delivered keynotes, lectures, and invited talks on advanced and hybrid machining technologies and Industrial 4.0 driven manufacturing system. He is a recipient of several prestigious recognition, including the National Educational Excellence Awards and the Dr. Radhakrishnan Best Teacher Awards and the Young Scientist Awards in Mechanical Engineering. His current research aims to develop intelligence and sustainable manufacturing solutions allied with that Industrial 4.0 and next generation productions technologies. I warmly welcome to today's section, sir.
Yes, sir. So, thank you for the brief introduction. First of all, I would like to thank the Institute, Tech Multitech, and the professors who invited me to deliver this keynote lecture. So, today's my topic will be optimizing hybrid technologies in machining. So, my lecture will be in two halves. One is I'll give a brief intro about what is hybrid technology, and later I will just give an intro about some optimizing process. So, the theme of FDP is actually AML. So without knowing the optimization, so we cannot go further on AI and ML. So this is the key fundamental which everybody has to work out. So that's why first I splitted my lecture into two halves. Maybe in future I will be continuing with the lecture. So I think my screen is visible. I'll just move on. So basically, my area is machining. So in machining, I will be explaining about what are hybrid technologies. So we know that there are three categories of manufacturing. One is formative, where if you require high volume of manufacturing which has to be done. So like your injection molding and all those things comes under formative. So where you just give some deformation to your material and you just form the final end product. So those categories comes under formative. And then we have additive. So recently it is very popular. We have many types of additive manufacturing for polymers as well as for metals. And wherever we expect high degrees of freedom, we have to choose additive manufacturing. So some complex shapes, some difficult geometry. So all these things we have to go for additive manufacturing. And by conventional, the next category is subtractive manufacturing, where all our CNC milling, drilling, boring, reaming, tapping, everything comes under this subtractive manufacturing. So this subtractive manufacturing has to be chosen when you need a high precision. So basically, we have to choose the right manufacturing process for our manufacturing of our product. So this is the basics. So as I told you the classifications, so my area first in this lecture I will be talking only about the subtractive manufacturing because additive manufacturing is a next new topic. So I will be just focusing on subtractive manufacturing. So basically we know a normal subtractive manufacturing we have turning, drilling, milling and some other operations. So in mechanical machining, we have these categories and there are some non-traditional machining categories also. So in non-traditional machining, we have other categories like we can classify into four different types. One is by using mechanical energy, that is ultrasonic machining and water jet cutting. So it comes under mechanical energy process where you use mechanical force to remove the material and to create an end product. So these things comes under non-traditional machining. And then comes your electrochemical process where ECM comes into picture. So electrochemical machining. So we use some chemical substance and electrical current. So it is an electrochemical process through which we remove the material. And today advancedly you would have noticed like some new technologies like biomachining. So where they use bacteria and they do like lithography process and they remove the unwanted material. So it is called as biomachining, which is recently very popular. And in India, only some 3 to 4 members are working in biomachining. So it is the demand is very huge, but not more scientists or faculties who are working in that area. So in abroad, it is very famous actually, biomachining, because we need the help of chemical engineers and biotechnologists to do this machining process. So it also comes under this non-traditional machining. And then comes the third category, which is called a thermal energy process. So we use some thermal energy, that is like heat. So it can be either from electron beam or from laser beam or from plasma beam. So we use purely thermal energy to remove the material. And finally comes pure chemical machining without the electricity. So we have these types of non-traditional machining. So maybe you would have recently gone through many papers which addresses either traditional machining or non-traditional machining. But my area is about hybrid machining because in conventional machining process, what I have discussed now, we cannot achieve a very high precise machining. So suppose you expect that in your component you need a accuracy level of 10 nanometer. Okay, so it is not at all possible by either using non-traditional machining or your conventional drilling or milling. So 10 nanometer precision is very high in demand. Similarly, if your material removal rate should be approximately 10 power minus 3 or 10 power minus 4 mm cube per second. So it is not at all possible by your conventional subtractive machining. So this is the objective first you have to fix. Why I am doing a work and what is my target of precision level. So as I earlier told, if you need higher precision, you should go for subtractive machining. If you need higher degrees of freedom, you should go for additive manufacturing. And if your number of samples is high, then you should go for formative. Right. So our objective in subtractive machining is precision. So you just have an objective that what is the precision accuracy you are expecting and how it can be approached. And what type of subtractive machining you have to choose to achieve this high accuracy level. But whatever we have discussed so far, like your normal drilling, milling, and boring, and your non-traditional machining like mechanical energy, thermal energy, electrochemical energy, we cannot achieve this high precision. So that is where this hybrid machining comes into picture. And suppose there is one more factor that if you want to integrate the positive and negative of different process. For example, you know that when you go for a grinding process, normally we choose grinding only when we need a surface polishing. And when you go for lathe, so lathe will be done for cylindrical objects for certain output. So we can integrate these types of subtractive processes, that is called as hybrid manufacturing or hybrid technologies. So for a researcher, so please don't expect only conventional machining or conventional manufacturing process. You create some new hybrid technologies so that you can achieve a better accuracy level through subtractive machining. So for an example, you just see this picture. The first picture I think you can see, it is a 15 micrometer hole. So the hole is drilled in a material. Uh, can you identify that material? So it is in black color. So can anybody identify that material? So what is that material is? The first picture which is shown where the drilling is 15 micrometer. So can you identify? Can someone identify that material? Yes. No response. Am I audible?
Yes, sir, you are audible, sir. Your voice is audible.
Maybe they are not interested, I think so. Okay, I'll just continue. So the first picture is human hair. So you can just imagine what is the size of our hair, human hair. So we have done drilling in the human hair. So the diameter is 15 micrometer. So you know what is the property of your human hair, how flexible it is. So you need a fixture design to hold that, and then you have to do drilling. So these are all the challenges. So when you address these challenges, that becomes a good research. So first to do a research, you need a challenging problem. So merely don't choose some material, choose some process, do something and write paper. That is not a good research actually. So you have to create what is the objective, what precision level you expect, and then you formulate what are the challenges you have to do the conventional process, either subtractive machining. In subtractive machining, a normal drilling process. And then you find out which subtractive machining or which hybrid technologies you can choose to get this precision level. So my precision level here is 15 micrometer drilled hole. So this is the first task. Now you just see the second picture. Can you see the gears, how it has been formed? So you can see the size of gears. You compare with the matchstick. So this is the precision level you should achieve through this subtractive manufacturing. So which is not at all possible by your conventional mode. Either you go for drilling, milling, reaming, planing, whatever you choose, you cannot achieve this. Even you cannot achieve this by using your non-traditional machining. So that's where you have to prefer some hybrid technologies. So you should have a clear objective, clear target, what is your precision level, and then you choose which process can be selected and which hybrid technologies you can mix it up, and then you just face the challenge to create this product. And the third picture, can you see? It's just a zebra, but you just see what is the micron level. We have created this in 80 micrometer sheet. 18 micrometer, that is 18 to 10 power minus 3. A very thin metal sheets, we have created this. So we have used biomachining actually. So earlier I told you about biomachining. So we have used biomachining to fabricate this third picture. So there are many other technologies in hybrid machining. So one by one, first I will just inform, and then later I will be moving on to optimization. So in hybrid machining, there are several types. So the first type is actually sequential. Sequential is nothing but with the name itself you can understand that the process will be in sequence. So first you complete one process, and then after completion you proceed with the second process. For example, you do turning, you remove the material, and then you go for milling, you remove the material, and then you go for drilling, and you get the final product. So this is a sequential type of machining. So after completion of the first part, it is being moved to the second process. After the second process is over, it is being moved to the third process. So this is called a sequential type. So it is not meant that it should be only in machining. Like you can also couple like one machining. The second process is welding. So you can see this paper which we have published in Material Chemistry and Physics in Elsevier. So what we have particularly done is we have done hybrid technology between abrasive water jet machining and welding. You just imagine. So we have just merged abrasive water jet machining and welding. These two are completely different process, but we have created a hybrid technology by just making abrasive water jet machining and welding. So this is the innovation to achieve the desired target. So that publication won't be a big matter. So we can easily publish. The only thing is we should achieve our objective. So first clearly define what is your objective. You should have some challenges. Without challenges, please don't select any research topic. Otherwise, it is very difficult to publish. Maybe some Q2, Q3 publications you can make, but Q1, if you want to achieve some Q1 papers, then you just target on a very challenging work, and you just do some hybridization like as we did. So this is the first example what we have done. So the first thing I've told you about sequential. The second one is called as assisted hybrid machining. So we have some assistance. So for example, if you are doing a drilling process, you can make vibration to assist your drilling. So in drilling, you can see that the tool will also vibrate and it will also do the drilling. So it is vibration assisted drilling. So there are many other processes like this. Laser assisted. You can see the examples I've just quoted. Laser assisted, vibration assisted. You are just, these technologies will assist you to do the normal process. You choose lathe, you choose phasing process. In that you can make laser to assist. You can make abrasive to assist. So these assist will help you. This is called as assisted hybrid machining. So I think it is clear now. You can also make some media to assist. Like you can make cryogenic assisted or gas assisted. I think everybody are familiar with MQL. Okay, minimum quantity lubrication. So MQL assisted. So you can imagine or you can frame your process like assisted manufacturing or assisted machining to do your task. For example, you can see this, one of our paper, it is published in measurement. So with the title, I think you can see, it is ultrasonic assisted EDM. So I think EDM machining everybody knows, okay, electrical discharge machining. So the one which we preferred is die sinking EDM. In EDM we have two different types, one is die sinking EDM and the other one is wire wire cut EDM. So we have preferred die sinking EDM, and we made ultrasonic to assist. So for to create the ultrasonic, you can see that we have used a lagging wave in transducer. So you can see in that picture, bottom right. So we have used the transducer to create the ultrasonic frequency and to do the EDM process. So we have made an assisted machining. So conventional EDM, I think everybody would have done. We have made a ultrasonic assisted machining. So this is the novelty, so that you can make your make use of creating a new process, and then you can achieve your target very easily. And publication has it actually comes out of this. Okay, so no need to worry about publication. It actually comes because it's a new technique. You are addressing a new novel process, and your objective is clear. Your novelty is clear, so publication automatically it will come. So this is the example for assisted machining. And one more example I'm showing you here, which is published in Precision Engineering, again Elsevier. So here you can see it is also ultrasonic assisted elliptical vibration to create a group. So we are just creating a elliptical vibration to create a micro group. So the micro group dimensions it is given in the picture, and the depth. So we have just created a comparison between without ultrasonic how the precision level was, and with the ultrasonic how was the precision level. So that's it. So you can just compare what happens when you do an assisted machining. So these are the examples of assisted machining. And the next type of hybrid process which you can make is you can combine two hybrid technologies. So for example, you can see here it is, you know about chemical machining, you know about electrical machining, you can combine electrical and chemical machining. It is called as electrochemical discharge machining. So that is nothing but in EDM you mix chemical. Okay, so that is the difference. So you have combined two techniques. You are not assisting or you are not doing sequence here. You are just combining two different techniques. You can see the second example, laser. Laser is a thermal machining. I think you would have noticed in non-traditional machining process, by using thermal energy, if you do it comes under laser machining. And in non-traditional machining, you have one more category which is called as electrochemical machining. You can make it hybrid in such a way that you can mix laser as well as electrochemical and create a new technique. So that is a hybrid machine. You are just merging two different process itself. So that can be done to achieve a better output. So why this is required is, see, laser has some drawback. The heat effector zone will be high. The surface property will degrade. The TMA is that also will be high. So there are many drawbacks in laser, but the temperature gradient is very good. So there are some advantages also in laser. But when coming to electrochemical machining, the finishing will be very good in electrochemical machining, but the process will be very slow. But in laser, the process speed is very high. So when you combine these two processes together, the disadvantage of one process will be overtook by the advantages of the other process. So finally, the disadvantages will come down and the advantages will just move on. So this is why we just combine two different processes. So you can see the next one, electrochemical grinding. So everybody know that grinding is a conventional process, and you know that electrochemical is a non-traditional process. So I am just mixing it up like a conventional grinding with a non-traditional machining like electrochemical grinding. So these ways you can imagine and you can couple these two processes to create a hybrid technology. So this type is called as combined hybrid machining. So some examples I can show you. So this is an example which we have done, which is published in Journal of Alloys and Compounds. So you can just see the title, Rotary Ultrasonic Machining in a Cryogenic Environment. See, cryogenic comes under assisted machining. So I think second category, if you have listened my lecture, the second category comes under assisted machining. where you can assist cryogenics, where you can assist LN2. So that comes under assisted machining. I've used drilling here. Drilling is a conventional machining, and I've used ultrasonic. Ultrasonic is also an assisted machining. See, I've just coupled three different uh, machining process to create a ultra precision product. So this is how you can merge different processes to create a component. So ultimately the novelty is good. You are developing a new process. So the objective is met. So publication doesn't matter. So just for your information, this paper is being published in just 12 days. For example, if I am submitting on day 1, March 1st, this paper is accepted on March 12th. Okay, so that is the duration of this acceptance of this paper. Because the editor itself directly he accepted without sending it to review. So this is our first paper which we got, like without sending to review, this paper was accepted. The impact factor is 6.3 and it is an Elsevier journal. Because the novelty is good, objective is clearly defined, the precision is met, and the paper is published. That's it. So these ways you have to think actually. So just don't think like publishing a paper is just like that, doing some experiments and moving out to write paper and putting into 10 journals, 15 journals. Every time it gets rejected and then finally published in some different journal. So don't work it in that way. You have a clear plan so that publication becomes easier. So this is one of the other work you can see here. Micro drilling of some composite. You leave the material by using hybrid micro ECDM. What is that ECDM is? Electrochemical discharge machining. I think you know about EDM, you know about chemical machining. I have included both chemical machining and electrical discharge machining. So once one use chemical energy, one use electrical energy. Both are different process. So I am just combining both and then I am just doing the process. So we can make these types of papers. So finally my first half is over. So I have just generally introduced about what is hybrid machining. So normally hybrid machining you have to do when you have to reach a high precision level. So whenever your RA value should be very high, so you have to go for that. And recently there are many processes which are used in hybrid machining where the improvement is around 30%. So that is achieved. So please try for some hybrid process like this. So this is the benefits of hybrid manufacturing. Okay, I'll just skip this. Okay, my second half is about optimization. So I think first I will just tell you why this optimization is, and then maybe slowly I will be moving on to what are the different types. I think everybody knows this, but how to approach a problem, that is the key thing I will be informing you now. So in industrial evolution, I think we have several industrial evolution, and currently we are in industrial evolution 4, but we have 5.0. 5.0 is already discussed in 2022 itself. It is not new actually, but still we are not used to this industry 5.0. So if you can address based upon this, then your research will be highly acknowledged. So what is industry 5.0? So you have to work with the computers. Okay, so the intelligence of human and the backbone of your skills of the computers. So it has to be cooperated and it has to be used. That is industry 5.0. So man and machine has to work together. So actually this discussion was held in April 27th of 2022 and still it is in discussion only. So this is about industry 5.0. So according to this, we have digital manufacturing. I think you would have heard about virtual manufacturing. You would have heard about digital twins. So you would have heard about IoT. So there are many processes which you can adapt in addition to the technologies whatever we have discussed now. So like your hybrid machining, by implementing a digital manufacturing process to create a better product with high precision accuracy. Your title can be in this form. So you can implement some digital manufacturing concepts to achieve your objectives. So that can be done. So IoT, I was talking about IoT, I was talking about digital twins. So all these things will support your experimental data. See, please don't think that IoT, digital twins, and all digital manufacturing is your work. It supports your work. So you just have that in mind. All these informations, when you just do research, please use this as a supporting information for your experimental work. Don't just believe these digital manufacturing values or IoT values. It should be an add-on for your experimental work. Then only your paper or your research will be at higher level. Okay, now coming into the optimization part. So we have two different types of optimization. Normally, what everybody does is the process optimization. So normally they just change if you are doing machining, they just change the speed, they change the feed, they change the depth of cut, and then they just study. They do different types of experiments, and then they do some optimization process, and then they publish a paper. It is like a black box. So you cannot publish nowadays. If you use some basic formulas or if you use some basic process optimization, it is very difficult to publish. You cannot publish in Q1 journals. Maybe Q2, Q3 you can publish, but please try your target should be at higher level. Please publish only Q1 journals. So if you do process optimization, you have to implement this ML technique, AI technique. So which previous lectures you would have heard about what is ML, what is AI, and what are the different techniques. Maybe in future FDP sessions also you will come to know about different technologies. But the only drawback in AI and ML is you need more and more data. You cannot just merely do with the 30 data or 50 data or 100 data. You need thousands and thousands and thousands of data. So it is very difficult when you do an experimental work. But some cases you can publish with those data, but be careful that if somebody reports that with minimum data, if you use AI and ML, and if they complain that this process won't be of acknowledgeable level, then your manuscript is highly risk. It can be retracted also. Because you cannot publish a paper with AI and ML with just with some 10 to 15 data. You should use thousands and thousands and thousand number of data. Getting these many number of data from a normal machining process or any manufacturing process is very difficult. So you have other techniques to maximize or to improve your size of data. So that process you have to make first. So that can also be done. You can officially report that I have used this technique to use several data, and then you take the data to AI and ML. That can be done, but don't just publish with some 10 data. Don't train your model with some 7 data and don't test it with the 3 data. The result will be wrong. The error value will be very high and the MPA value will also be very high. So please don't do that. You generate the number of data. There are many models available to generate or to improvise your data, number of data. You use that model. You write it clearly in your manuscript that this model is being used to maximize my input data. You clearly give how it was manipulated and how it was improved, and then you take that output. Maybe you will have some 10,000 or 50,000 data, and then you train your model, and then you test your model, and then you report what is the value of MPA, error values and other mean values. So this is how you have to go for AML. But optimization doesn't require much amount of data. With some mere 15 data, 20 data, 100 data, you can do optimization. Because optimization will just give which value is good. That's it. If you have 100 data, it will tell which is good. If you have 200 data, it will tell which is good. That's it. So even if you have 2 data, it will tell which is good. So here the approach is different. AML approach is different. So please don't mix it up with optimization and your AML. So both are different scenarios. Okay. So first I will address the optimization process. So in optimization, you can do either process optimization or a product optimization. In process optimization, like everybody does, you change your speed, your feed, your speed, depth of cut, you measure your tool life, you measure your tool wear, you measure your surface quality like RA value, RB value, RQ value, whatever it is, you just measure that. You measure what is the temperature effect, you measure what is surface tension, surface stress, you calculate what is machining time, you calculate what is cost, you minimize that by using some process, by using some models, then it comes under process optimization. But if you switch your objective to product optimization, the possibility of acceptance of your paper will be very high. For example, you can use an OEE technique. That is, I think everybody know what is OEE. You can use an OEE technique to improve your product efficiency. You can use some lean management, lean time management to improve your production. You can use some optimized process planning, like your path. In some factories they do like path planning, process planning. You optimize that process, that entire process you have to optimize. That comes under a product. So the entire manufacturing product, if you optimize, then this.
We will start out.
விமல் சார் ஏதோ உங்களை பத்தி பேசிட்டு சொல்றாள் தான் வந்தாலே ஆனா இன்சார்ஜ் சொல்லுவார் பஸ் சொல்லுவாரு அவன் போனானா அந்த இடத்துல கலவட்டு முட்டி மூணு வடையை சாப்பிட்டு இங்க நடக்கிற முக்காவாசி பிரச்சனைக்கு அவர் தான் காரணம். வெளியுறவுத்துறை அமைச்சர் ஈரானோட வெளியுறவு எப்படா சொன்னீங்க எல்லாமே கட்டிருப்பான். 5 நாள் வச்சுட்டா ஒரு நாளைக்கு 6 பேர் வச்சுட்டா 90 பேர் வச்சு பேசிருக்கே. டீச்சிங் ஆண்டிங் எல்லாமே வா டீனு கொஸ்டின்ல இருக்கணும் டீனு பிரின்சிபாலா அபிஷியல் மட்டும் தான் அட்டாக் பண்ணுவியா?
Sir, is it okay? Shall I continue? Hello?
Sir, you may continue, sir. Sir?
Yes.
Yeah, yes, sir. Okay.
So you can just switch to this product optimization or manufacturing process optimization. So a better example. See this. I think everybody know about hydrophobic effect. So the best example is your lotus leaf. So I think you can check what is an hydrophobic effect and how this happens in the lotus leaf. So what actually the recent research is going on is you can create the same pattern of the lotus leaf in any surface so that you can create the hydrophobic effect. So the right side you can see some examples. In car windscreen, they have created a similar structure of lotus leaf. So there will be a paint which when you apply over the windscreen in your car, so the surface morphology will be similar to that of your lotus leaf, so that whenever you have rain, so the water droplets won't stick on your windscreen. So you no need any wiper itself actually. So this technology is a research actually. So recently, now you would have seen many ads like Blue Island. So they manufacture shirts and trousers. So they created this microstructure of the lotus leaf in shirts and trousers. So what happens is you can compare the two pictures. So one is a normal shirt and trouser, and the second picture is the pattern of lotus leaf is being implemented in this shirt and trousers. So that creates a hydrophobic effect. So what happens normally? So when you just like that walk in the rain, what happens is you won't have the water droplets sticking in your shirts or trouser. It just slides out. So this is the research is happening. So what we can do, everybody know about this, but what we have done to this, you try to implement this structure in your tool. We have tried this. We have created this pattern in tool, like your cutting tool, in your lathe, in your drilling, in your milling. You try to create this pattern of lotus leaf in the tool. Okay, sir, what happens when we create this pattern in tool? See, whenever you have this in tool, the lubrication efficiency will go up. So when you go for assisted machining, when you go for MQL, the wettability will be good. So when you have higher wettability, the tool temperature will come down. So when the tool temperature comes down, the tool life will be good. You can just calculate what is Taylor's tool life equation. With that, you can calculate and you can report that the tool life will be good. The fracture of the tool will be less. So the machining efficiency, when you calculate, it will be high. The cost will come down. So you have several benefits when you create this microstructure in the tool. So this work actually we have done. We have tried this. Okay. So I think many disturbances.
Now, clear.
So you can make this. You see your imagination should be wide enough to implement whatever you see actually. So we have actually done this. You can see here. So as I told you, we have took a conventional tool and we have created the pattern. So you can see the second picture. We have created a micro groove. So which is a similar effect of the lotus leaf. And then we have done machining through that. So we have found that the temperature gone down. So the total tool life was improved. So if the increase in tool life, what happened to the tool wear? Tool wear comes down. So these things we can address. And this is a novelty which actually the research expects. So you can clearly frame your objective that this is my target. So my objective is to create a hydrophobic effect and to increase the wettability in my tool. So that you clearly describe in your paper, in your manuscript. And this is how I am going to address this. So we have proof and many are doing with this. So then you just clearly give what is your literature review, and with that literature review you address your problem, and then you can see this one of our paper which is published in Materials and Manufacturing Process. See, the first picture shows you our tool insert, surface texture tool insert. Okay, so we have created a pattern in the tool insert with some spec, and we have reported that, and we have done the machining study. A normal machining study. We have not took some composite material, something normal steel. You just buy a steel, conventional 1045 steel, and then we have just done the milling by using a patterned tool. Okay, so this pattern tool is nothing but based upon the hydrophobic effect which we got through the lotus leaf. We created some pattern in the tool, and then we have done this. So what finally happened is the thrust force came down. So I think those who are doing in machining, maybe you know what is thrust force. The thrust force came down. The tool tip interface temperature came down, and then the tool wear was good. It was less, and the tool life was good. And a higher precision level we can achieve on the surface of our material. So these things we clearly reported and our manuscript was accepted. So this is one example. So you can see the second example, there are many patterns you can make. It is not a conventional like only the replica of some lotus leaf. You can make any pattern in your tool that can be done. You just see the pictures what we have done. A circular pattern. Can you identify the second pattern? It is nothing but your semicircle. Okay, like a semicircle, a lighter. In the Diwali light pannuvoomla, so it is similar to that. Okay, it is a lighter. You just in your imagination, whatever shapes you think, you just create that pattern. So anyway, the wettability will be good. So people nowadays, people what they do, they create different types of patterns, different type of structures like this, and they just do the machining. And finally, they report that the process is good. Okay. And the next one is, see, the first inspiration was from the lotus leaf. Our objective was hydrophobic effect. Just a minute, it's noisy. Just a minute. Okay, sorry. So the second inspiration is from mosquito actually. See, you know the mosquito needle. Okay, when you bite, how you feel actually? Sometimes you can feel, sometimes you cannot feel. It will just come and it will sit on you. It just sucks blood and it just leaves. Sometimes you can feel, but sometimes you cannot feel. So what you can make the structure of that probe in a real needle. நம்ம டாக்டர் யூஸ் பண்றாங்க needles. அந்த needle if we can make this type of structure, what happens? ஊசி போடும்போது வலிக்கவே வலிக்காது. So nothing will happen. You cannot feel that pain itself because the same thing happens with the mosquito also. So this also happens because of the inspiration from the mosquito. So that can be done. So you can see the pattern. So just take the probe of the mosquito, you check it in your microscope, you take that pattern, you replicate this pattern in your drill bit, okay, or your lathe bits, and then you do the machining, you create the same pattern in the needle, and then you test it. So this is how the research has to be. So similarly, there are many inspirations you can see. So I've listed some. So electric eel inspired stretchability. If you can inspire from electric eel, so electric eel has a good stretchability. So you can inspire and you can create a component by inspiring from this electric eel. An octopus inspired adhesive ability. You know what is adhesive? How the suction cup of the octopus. So you can inspire from that, you can take that model, you can see how that high suction is happening, and then with that knowledge you can create a adhesive material so that is inspired from octopus. And elephant trunk inspired structure. See, normally you see na elephant trunk, it can just like that, it can lift a huge tree, okay, huge block of tree. But it doesn't have bones, only muscles. What is there in elephant trunk? That should be an inspiration to create a structure which can have a high strength. So it has to be inspired from elephant trunk. A bird inspired bullet train. So you can see the bottom picture. And gecko inspired tapes. I think you know gecko. Onam, Palli, it comes under this category. So it just like that it climbs the wall without any suction curves, without any difficulty, just like that it climbs. What happens like we create a suit with the like the technology what gecko uses, really you can become like a Spider-Man. Okay, so you can just climb on the wall. The inspiration should come from here. So nowadays what they do is they just create tapes. Okay, so it can stick on any wall. So it can stick on glass, it can stick on wood, it can stick on metals, it can stick on plastic. So the inspiration comes from this gecko and peacock feather inspired material. What happens when you inspire from peacock feather? So peacock feather, I think you know. So it gives multiple color based upon the reflection of the sun rays. So a single material, a peacock feather, it can reflect different frequency of light rays. So you can see red, you can see violet, you can see blue. So it reflects different frequency of light rays so that you can see different colors. What happens when you create a material with this inspiration? Your material will be like your peacock feather. It can reflect all colors. It will be like a rainbow. So these effects has to be inspired. So these technologies also you can have a target, you can create an objective, you find out a solution. Yes, that is a good research. That can be done. Okay. Then coming to the optimization, as I told you, two types. One is process and product. So we have published some papers. Just to have a clear idea, I've just shown two categories. The left category shows you the process optimization, and the right category, right side, I have listed two papers. It shows you about product optimization. So first I'll start about process optimization. You can see the left side. So it is a normal viridium process. I've used some gray relation technique. It is a very old technique. The paper is published in 2015, but nowadays you cannot publish papers by using this technique. Okay, so there are many other techniques. So please don't choose this. I've just quoted because of tell you that we have done process optimization. Okay, but please don't use this technique nowadays because it is 11 years from before. So earlier it was a good technique, but nowadays almost it is dead actually. Okay, and the second paper you can see that it is published in alloys and compounds. Again, we have used some process optimization to optimize the roughness. So again, please don't use this regression and desirability analysis. All these are very basics. You try to code some. See nowadays we have ChatGPT, you have Python. You try to code with the data whatever you have, and then you can use that code for publishing. Don't merely use the conventional techniques like earlier they used not some Taguchi technique and gradation, and you don't use some regression analysis. Don't use RSM. So these are very old techniques. So manuscripts require new techniques, new concepts, new optimization algorithm, new technologies. So please address something like that to make your paper accepted. So these things comes under process optimization. And then you just see the second half, right side, which is published in Springer. So we have optimized the tool geometry. I'm not optimizing the process. Like I'm not finding out which is the best surface finish, which is the best material removal rate. I'm not optimizing the process. I'm optimizing the tool itself. What type of tool geometry I have to use to get a better output. So this comes under product optimization. So you need more and more tool information. You should know about tool nomenclature. So all these aspects will help you to write a paper on that. So you can work on that. Or the next paper you can see I've used finite element modeling for optimizing the process. So you can use FEM, you can use some other softwares like Abacus, you can use LS Diana, you can use some other softwares to optimize your process. That can be done so that your acceptance rate can be very good and your research also it will be very novel. So these things can be done. So this is how you can segregate. Okay, my final part is just to tell about the different optimization. I think everybody would have an idea about this. So the first category is natural evolution. So you have genetic algorithm, which is very old. It is around 1960 they invented about genetic algorithm, and then comes under environmental adaptation method. It is very recent. So please focus on this algorithm because the founder of this algorithm is only 2018. Not much paper has been come under this environmental adaptation method. So please concentrate on newer optimization techniques. You have many sources. You use GitHub, you use ChatGPT, you use some coding from some AI tools, and then use those technologies for your process. You create a program, you analyze it, and then you can report. That can be done. But when you use an open AI, please mention in the declaration that I have used this open AI to perform this task. Without declaration, please don't submit your manuscript. Declaration is very, very important. In declaration, you have to write that this is the open AI I have used to do this task. That has to be reported in declaration, and then you have full freedom to publish your work. Please report that in declaration. And also, please don't use ChatGPT as one of the co-author, because nowadays I can see many papers like the first author will be Kumar, second author will be Suresh, third author will be ChatGPT. Please don't do that. Okay, so you use OpenAI, you create you create your programs, but you should write in declaration. Okay, so this is a new technology which you can use. And then comes biological based algorithm. I think everybody know about frog leaping algorithm and flower pollination algorithm. Flower pollination algorithm maybe not much have been used, so it came only on 2012. So maybe you can try flower pollination algorithm. And some other algorithms like teacher learning bus algorithm. They use these algorithms for overtaking of cars and to learn and repeat the process. For those things, they use this teacher learning based algorithm, and they have J algorithm. Okay, everything is new category. J algorithm is came only at 2016. So they have many different types of algorithm like this. And then you know about swarm intelligence. Maybe the previous session also they have discussed about particle swarm optimization, ant colony, firefly. There are many other optimization techniques available, but make it limited. Okay, don't use these widely in your paper. See, optimization, as I told you earlier, optimization should add value to the manuscript. That's it. But the core work should be your fundamentals, your objective, your precision accuracy, how you are achieving your objective. That is your main target. You use this optimization as an add-on to just verify whether it is right or wrong. That's it. Don't use like an overdose. If you use overdose, simply the reviewer will give like the manuscript is like a big black box, so we cannot accept these types of manuscript, or it is not in our scope. Okay, some 80% you use your technical skills, technical output, technical stuff, and then 20% as an add-on with some algorithms like this. And science-based algorithms we have like gravitational search algorithm and water cycle algorithm. You know water cycle, like evaporation, condensation, and then it forms rain. So with this pattern itself, we have an algorithm. That type of algorithm is called as water cycle algorithm. So you can use those algorithms. And swarm intelligence, you can see the year when it came. Ant colony algorithm, it came in 1992. It is very, very old, but still many persons are using that. If it is really required to find out, then you go for ant colony optimization. Just like that, don't implement that. Yes, I know ant colony optimization, I will use in my paper. Please don't go in that fashion. If it is really required to get some output, then you choose these types of algorithms. Similarly, PSO in 1995, artificial bee colony is 2001, firefly is 2008, and the gravitational search algorithm 2009, and water cycle algorithm is 2012. Maybe you can just look into this. So these are the many different types of algorithms, optimization algorithms which you can use. So why I am more focused on optimization algorithm rather than AI and ML is, as I earlier told, AI and ML is only meant when your data set is very, very huge. Please don't use AI and ML for minimum data sets. Data sets should be more than 10,000 or 100,000. Then only you can go for AI and ML. Your error will be low, your precision will be high. You will get a better output. But whenever your data set is small, please go only for optimization tools. So how to improve your data set? You cannot improve by your experimentation. Just like that, conducting 10,000 experiments in lathe, it is not at all possible. Please don't that. Don't do that. There are certain algorithms which you can use to improvise your data sets. That can be done, but it should be properly reported in your manuscript that this is the algorithm I have used for improving my data sets. That is legal, that can be used. So first you improvise your data sets and then you go for AI and ML. So that can be done, yes. So that's why I'm just more focused towards optimization algorithm. So finally, the future prospects should not be only conventional machining. It should be hybrid technologies, as I told you, either sequential or assisted. So it should be in any one of the form, or you have to inspire from nature. Like I've shown you about lotus leaf inspired tool, and the other one I've shown you about mosquito needle inspired material. Okay, so you inspire from the nature, that is called as biomimicry. You can just search Google Scholar, like you put this term biomimicry. There are lots and lots of papers in this biomimicry. Please start working on this, and please focus on quality and improvement of production, not the process. Process optimization and process leverages everybody would have done. But please, you divert your research work towards quality improvement and productivity improvement, or production in less time and less cost. Please divert your research work, or you just go for hybrid machining. And please explore this biomachining, because only 4 professors in India, they are working on biomachining. So please explore this. So nobody in India is working on this biomachining, but it is very difficult actually. You need a biochemist, you need a chemical engineer, and you need a mechanical engineer to work on this biomachining. So it should be an interdepartmental, and then you can work on this biomachining. You clearly define what is the objective, you frame your work, you fix your precision level, and then you choose your material, and then you try to address your objective and to achieve the desired target. That can be done in biomachining. And then you can adapt some technologies like digital manufacturing, IoT, AML, or optimization. You can adapt any technologies, but it should not be dominant, as I told you. So as a manuscript, they expect only technical knowledge rather than this AML content. You can add AML just to improvise your output, but not to just show off your paper. I've done AML. Please accept my paper. No, it is not just for your show off. So it is only for an add-on to improvise your results. So please keep that in mind. So that's it from my side. So this is my contact. So any more doubts, I'm ready to address.
So dear participants, do you have any questions? So kindly ask to Dr. Yes, Tirumali Kumaran. Professor, there is no question from participants. Shall we conclude it, sir?
Yes, sir. So thank you for the organizers who invited me to give this lecture, and I also thank the Tech Multitech for providing me this opportunity. I'll be more thankful, and anybody can contact me for any useful tips. Thank you, sir.
Thank you very much, sir, for the highly informative and insightful session. Your valuable presentation on optimizing hybrid technology in machining, in which you have the participants gained different types of hybrid technologies and assisted hybrid technologies, along with the different optimization tools. So that has certainly provided new perspectives for all the participants. So once again, on behalf of management and organizing team, Department of Mechanical Engineering, Welltech Multitech, Dr. Rangarajan, Dr. Saundula Engineering College. I extend my sincere thanks to Dr. S. Thirumalai Kumaran for sparing his valuable time with us today. So with this, we come to the end of the day 3, session 5 of the FDP. So thank you all for joining us. So we will meet again in the afternoon 1:30, session 6. Thank you, Professor. Thank you, dear participants.
Yes, sir. Thank you.
Yes, thank you. Participants, you may leave the session.